Hello everyone, this is Miss Lindsay. Today we're going to continue on with section 12.7, dealing with exponential and logarithmic equations, but specifically we're going to deal with word problems today. Our first example is a type of compound interest problem. As you can see, we have the formula here, A equals P times the quantity 1 plus R over N raised to the NT. Now this is a slightly different version from what's in your textbook. It's a bit more specific, okay? I want to point out a couple different things here. On the side, you can see that each variable is defined. R rate, I do want to point out that that is written as a decimal. And N is the number of times compounded per year. So let's go ahead and read the first example. Suppose 5,000 was invested at 7%, compounded annually, and it yielded $9,540. For how many years was it invested? So the starting amount, which is our principal, and our particular problem is 5,000, so we'll plug that in for P. Then we'll have 1 plus in our rate, which was 7%. Divide that by 100, so we write that in decimal form. And so in other words, we'll move it over 2 decimal places. So that'd be 0.07. And it's compounded annually. Therefore, it's going to be, N would be once, because it's compounded once per year. So N would be 1. And it yielded $9,540. That is our accumulated amount. So we'll substitute that in for A. And number of years is the variable that we are trying to find. So T will be simply T. Let's go ahead and simplify this. So we'll have 9,540 equals 5,000 times 1.07 raised to the T. This is an exponential equation, therefore we want to isolate the exponent. So we'll divide by 5,000 and get 1.908 equals 1.07 to the T. And again, think about how we solve exponential equations. If we cannot get the bases the same, we would like to take log of both sides. Therefore, we have log of 1.908 equals log of 1.07 raised to the T. Using our properties of logarithms, that exponent of T would go down in front. So it would be T times the log of 1.07. Now just recall, log of 1.07, this is something that we can plug into our calculator, is simply just a number. Therefore, we can divide both sides by log 1.07. So let's go ahead and go to our calculator and calculate this. So we'll have log, excuse me, 1.908, close our parentheses, divided by log 1.07. And again, close those parentheses. Let's go ahead and round to 1 decimal place here. So we'll round that to approximately 9.6 years. Okay, and just follow the standard rounding rules that are talked about in your book when you're doing each specific problem. The second type of word problem that we're going to be dealing with is with loudness. This is measured in decibels. Loudness in decibels of sound intensity, so intensity is I, is shown by the formula L equals 10 times log of the quantity I over I sub O, where I sub O is the minimum intensity detectable by the human ear. An example of that would be the tick of a watch. Okay, so let's try our first example here. Find the loudness in decibels of conversational speech for which the intensity is 10 to the 6 times I sub O. So plugging into our formula, we have L equals 10 log of, well, let's try to figure out what I and I sub O are. Going back to our problem here, the very last part, it says intensity is 10 to the 6 times IO. Well, intensity is I, so that would be equivalent to 10 to the 6 times I sub O. So substituting that in for I, so we have 10 to the 6 times I sub O over I sub O. When we simplify, you can see that the minimum intensity, I sub o, would cancel. So we'll get 10 times log of 10 to the 6. Using our properties of logarithms again, knowing that this is a base 10 when that is not written in there, that would then be 10 times 6, which would give us 60 decibels as our loudness. Going to our second example, which number 3, this is our second example of loudness. Here we have musicians can obtain special earplugs to avoid hearing loss when the loudness of a concert is in the range of 80 to 120 decibels. How many times more intense is the sound level at 120 decibels than it is at 80 decibels? So we actually have to calculate a couple different calculations here. The first one is when our loudness is at 120 decibels. And the second calculation will be when it's at 80 decibels. Okay, so let's first start with the 120. So 120 would be equivalent to 10 times log. It should be over the intensity divided by the minimum intensity. Well, typically, as you can see, going back to our second problem here, our intensity was defined in terms of I/O. This is typically how intensity is defined. So we will do that exact same thing in problem 3. We'll call that X times I/O for our intensity. And that would be divided by I/O. Just like the previous problem, the minimum intensities would cancel. So we get 120 equals 10 log of X. Divide both sides by 10 so we can isolate that log. So we get 12 equals log of X. This is a logarithmic equation. How do we typically solve that at this point in time? Convert it back to exponential form. So 10 to the 12th power would equal X. Now let's go ahead and calculate decibel when it's 80 decibels. So now we go through the exact same process where we have 80 equals 10 times log of X times I sub O over I sub O. The minimum intensities, I sub O, would cancel off. 80 equals 10 times log of X, divide by that 10, and then write in exponential form. Excuse me, I dropped my marker. So we have 10 to the 8th equals X. Let's go back and read the question. How many times more intense is the sound level at 120 decibels than it is at 80 decibels? So we need to find the difference between these two. So we'd have 10 to the 12th minus 10 to the 8th. Following our properties of exponents, when we have the like bases, we can subtract our exponents. So that would be 10 to the 4th. So in other words, that would be 10,000 times more intense. Moving on to our fourth example, which deals with the Richter scale. The magnitude R, which is on the Richter scale, of an earthquake of intensity I, is defined as R equals log of the quantity I over I sub O, where again I sub O is our minimum intensity, which was used for comparison. So looking at number 4 here, we have if the earthquake in Japan on March 11, 2011 was 8.9 on the Richter scale, we would like to find I, the intensity. So 8.9 will be our R. So we'll have 8.9 equals log. And again, we typically define intensity in terms of the minimum intensity. So we'll define I as X times I sub O. And we divide that by I sub O. Therefore, those will cancel off. 8.9 equals log of X. Logarithmic equation, convert that to exponential. So I have 10 raised to the 8.9 equals x. And since this is a rather large number, we'll just go ahead and leave it as 10 raised to the 8.9. So the intensity is 10 to the 8 raised to the 8.9 times I sub O. Okay. And our last example is a little bit of review of what we've been doing in the previous day of section 12.7. Let's go ahead and solve a times b raised to the x equals c for x. And if you notice, I have a hint here. We will need to take log base b of both sides. Take a moment, pause, ask yourself, do you see why we would need to take log of base b of both sides? Okay, there's a couple different approaches to this. The very first thing that we're going to do is we're going to follow our hint. We're going to take log base b of both sides. Following our properties of logarithms, we can separate on the left-hand side that multiplication into two logarithms. We're going to expand log base b of a plus log base b of b to the x, b raised to the x, equals log base b of c. Again, still following our properties of logarithms, we can do our down in front with the x. That will go out in front. So we'll have x times log of base b of b equals log base b of c. And we have one more property here. We know log base b of b would simply be 1. So that would reduce to simply x. And some of you actually might have noticed right away that you could skip this step that I checked here, because we have another property again. When those bases are the same, we simply would just get that to be x. Either process would work. They're both correct properties. Let's go ahead and solve for x. So we'll subtract log base b of a from both sides. And now condense on the right-hand side using our properties of logs. Log base b of c divided by a. Okay. All right, and we have solved both sides for x. So you can see x is equivalent to log base b of c to the a. Let's go back to the question up at the top. Do you see why we need to take log base b of both sides? And it is because we have b raised to the power of x. So we would need to get rid of that b. Okay? Some of you at some point in time actually could have maybe initially saw, okay, I have b to the x and I need to divide by the a. So at that point in time, if you do that, you have b to the x equals c over a, and then that makes it a little bit more clear that at this point in time you need to take log base b of both sides. This is actually a slightly shorter method, because if you take log base b of both sides there, you only have a couple steps and you get right to your answer. So let's go ahead and finish that. If we take log base b of b to the x, log base b of c over a, you can see again, using our properties of logs, we would just simply get x equals log base b of c to the a. So that is a slightly shorter method. Let me go ahead and move this over. So there really is two methods to that. The one in black on the left, or the one on the right in red. Both are appropriate. Okay, and this concludes the second day of 12.7.